So we start from science, and the title of my PhD work and my main project of my PhD work is the water-based renewable energy technology. So on this figure on the left, I didn't label it, but it is represent a hydrophilic material. So if you have a tank of water, you place the hydrophilic material in the water. Right next to the hydrophilic material, water forms a different structure. As a consequence of that unique structure, we know it stores net negative charge. And water, H2O, originally is electrically neutral. So it's easy to imagine beyond that interfacial water region, we have the bulk water region, which carries slightly positive charge. So we have charge separation, and the phenomenon is there. In order to measure it, all you need is a voltmeter. So the actual setup, still simplified version of the setup is this. So we have a tank of water, we place hydrophilic membrane at the bottom or anywhere you like it. And in this case, we use naphthalene. And we have two electrodes. One is the probe electrode, the other one is the reference electrode. The probe electrode just on the surface of the hydrophilic membrane in the interfacial water region zone, which AKA known as the exclusion zone. And the reference electrode just far away from the surface to serve the purpose as reference. We connected to an electrometer, which is nothing but a fancier version of voltmeter, has really high input impedance. We also connected in parallel with the resistor, and we're going to explain a little bit more why we need this resistor. So the main measurements, the first one, we actually have a step motor, so we can control the probe electrode to moving away or close to the surface to give us the electrical property profile of what's happened in the interfacial water region. So this figure here shows we have on the x-axis, the unit is micron, it represents the position. And 0 means right on top of the surface. 1,000 micron means a millimeter away from the surface. Red and blue, red is when you move the electrode away from the surface. The blue dots here, the blue lines here, represent when you move the electrode back to the surface. So we can double check if the measurement actually be consistent. So you can see at the top, just right next to the naphthalene surface or the hydrophilic surface, usually we get about the voltage around minus 100 to 200 millivolts. In this case, about 140 millivolts. When you move the electrode away, the voltage gets less and less and less, which means it's actually moving out from the interfacial water region. And this experiment is highly reproducible. I would say over 99%. If you don't break your electrode, you're going to measure the same profile. The second thing is, in order to know the power, the energy from such system, we made this IV curve. I represent as current in the y-axis, and phi represents voltage in the x-axis. The beauty of the IV curve is if you know the current and the voltage on this curve, so at any given point on this curve, you can calculate the power, just multiply the current and the voltage, then you get the power quite easily. So in this case, the maximum power output for single pair electrode, it will be 10 millivolts times 1 microampere, and that's 10 nanowatt. That's how we started. So for the majority part of our research, we play around with this system. We modify it, we do a lot of things, but we just want to show these things is reproducible and also the science is solid and legitimate. So the next question is how we scale up the power, because 10 nanowatt, you can hardly power anything. Before we go into more engineering and technology, to sum up the science, energy cannot come from nowhere. We identify it's actually the ambient infrared energy coming into water, give water has the chance to build the structure. And once you have the structure, the charge separation is more like a side effect, just a consequence of the structure. But since you have charge separation inside water, you know there's energy available. So our current approach is using 3D printing technology. The reason we use it, first, it's fancy, and second, it's actually really good for rapid prototyping. Everything is cheap and fast. So this is the graphic of one single cell. In this single cell, we have two pair of electrodes. The short tube, if you may, or electrode here, represent the reference electrode far away from the interfacial water. And the long electrode here represent the probe electrode just right into the interfacial water region. So we have anode and cathode. Just like battery, when you buy a battery, one stage AAA battery, when it's not powerful enough to power the electronic you want to, then you buy 2, you buy 3, you buy many, many more. You place them in series to increase the voltage, or you place them in parallel to increase the current. So we make an array of such electrode system, that's called electrode array. So we have, the top part is the electrode array, the bottom part is the water reservoir. In the bottom reservoir, you place the hydrophilic membrane at the bottom, and because you have wire and the electrode system, you just put them together, and then you can have energy. I played this video 2 days ago, but it's just really, really cool, so I want to play it once more. I hope it works. Okay. So still, here is the 3D printing prototype, rapid prototype. We have the electrode in there, water in there, just water and electrode, and some hydrogel actually. And here, just a switch. Behind the magnifier is an LED. The magnifier just make it look more visible. So when you turn the switch on and off, and on and off, you can see you power the LED by pure water. So that's kind of the demo we like to present to people, because previously, without any tangible and visible demonstration, it's really hard to believe you actually can power electronic by using pure water. So we're really excited about it. So many people ask me, and also I mentioned, the reason we use 3D printing model, because 3D printing technology, just for the sake of rapid prototyping, prior to using 3D printing technology, we actually start from MEMS. The MEMS stands for micro electromechanical system. It's basically the micro fabrication that we use to produce the chips inside our laptop in your cell phone. So it's a state-of-art technique, and by using this technology, we can make everything so compact, so small, in a way more energy efficient. So I just drew this kind of to show you the conceptual idea. So at the bottom there, we have a seed layer, which is the silicon wafer. There are so many details missing here, but just the conceptual idea. And on top of that, we have a metal layer. The metal layer just serves the purpose as electrode. We can use silver chloride as the standard material for standard reference electrode, or we can use noble metal like platinum or gold. On top of that, at the top layer, we have an insulation layer. We're using silicon dioxide. So when you have everything all together, just sandwich it together, we etch the hole in the silicon dioxide layer. So you have the metal exposed to air. Eventually, you're going to put in the water, and you can just grow the metal through the insulator, then it becomes electrode. The simplest way to do it is electroplating. You simply connect it to anode and cathode and run the electric current into it. You can grow the metal through the silicon dioxide. The problem for this design is it's too expensive and it costs too much time. So we're still currently working on it in order to make better efficient. I think eventually we'll go back to the MEMS technology. But still, for the sake of rapid prototyping, we're currently using 3D printing technology. And there are so many difficulties here because the variables we can play are, let's say, the material for the electrode, the design of the geometry, the material for the hydrophilic membrane, and also there are so many other things. So one thing, kind of the inside joke we always have is even we call it easy, but it's not easy. And the next step actually we try to do is try to commercialize it. So for the commercialization, of course, we want to get money, want to get power. Maybe you are thinking right now, oh, we are scientists. We don't want to be so superficial, talk about money and power. But just let me explain a little bit more. We really need money for the further research. Like the MEMS technology, every single design, since we not fully understand the science yet, so every single design, we just tweak a little bit on each variable. And every single design, it costs about $5,000 to $10,000 US. And it took me about 1 month for every single design. And once we have the prototype, we test it. If it doesn't work, oftentimes we don't know which part go wrong. So it's really hard. And money just for the further research. And also we need power. The power here is not the electricity, not the electrical power, and also not political power for sure. The power here is the manpower, or the brain power, if you may. Look around us, we have relatively small community for this kind of fascinating research. If we can grow the community 10 times more, I don't know how fast we can be, but it will be faster. If we can grow the community 100 times, 1,000 times more, then the improvement will be dramatically different than what we actually have right now. So when you have the money and brain power, we go to invest in more research. And better research yields better technology. Better technology provides more money and more brain power because people get interested into it, jump into this field of research. And it's a healthy, organic process. Even the figure shows kind of a smiley face here. You like it? I like it a lot. So because we talk about the commercialization, and the first market we identified for the power we can deliver right now, just in the demo video we show we can power an LED, and the output power is about 1 milliwatt, plus and minus 10 microwatts. It is actually useful already, not enough to charge your cell phone, but there are so many sensors surrounding us, and it's the trend to make the sensor become wireless. This is a very information-heavy diagram, so just ignore the wording here. The whole point is to show there are sensors everywhere in the building, in the room. For example, there are sensors in this room to monitor the temperature or humidity in order to run the AC system. And also, we'll constantly measure the vibration of the building to make sure it's secure and safe. Similar sensor we place it on the bridges, just to make sure the bridges are safe. You also have sensor in your car, even in your pocket, inside your cell phone. We have sensor in the ocean, on the boat, in the forest, in the park. So it is everywhere. And the current global market for just wireless sensor is about 2 billion. So the sensor doesn't sound very, by itself actually I think it's very interesting. But it's just gaining awareness, and I'm actually really surprised how big is the market. So to sum up the science and technology, we know infrared light energy is everywhere, it's ubiquitous. So it's really smart if we can use the most abundant energy on the planet, not just on the planet, in the universe, which is the infrared energy. We use water as the medium, convert that infrared energy into electricity. And currently, we can provide 1 milliwatt once again. We can power LED, we can power sensors, wireless sensors. The next thing we hope, within just a couple years, we can actually charge our cell phone. And what's next? Well, this is a solar charged car. If solar can do it, if photoelectric effect, more than 100 years ago, I believe it's 1905, Einstein presented the concept, the physics of photoelectric effect. I believe not many people can imagine we can use just the photoelectric effect to power the car, even power the house, even power the city. So the technology we're working on is just going to the same trend, and I believe it's possible eventually we can power the house and the city. Even it is still a dream, but we're getting closer every single day. So thank you.